In this example here, just like the last four, we are being asked to draw the products of the following acid-base reactions. Then we're going to label each compound as an acid, a base, a conjugate acid, or a conjugate base. And then we're going to determine the direction of the equilibrium. All right, so just like the last examples, let's figure out which structure here, which species here is the base and which one is the acid. Well, in this one, it's pretty clear that this is going to act as the base here. It is a species with a full negative charge. It's most likely the most basic one here. So we're going to go ahead and label this one as a base, and then we're going to go ahead and label this one here as the acid. So we need to now figure out which proton on the acid is the most acidic proton. And again, we can do this with the pKa method. We can recognize that this one here has a pKa of about 24. The rest of those protons in this structure have a pK of about 50. So we know it's going to be this one that's acting as the proton here that's going to get donated. Because the lower the pKa, the more acidic they are. But again, if you don't know the pKa's of everything, and you don't have to memorize these things, you can evaluate which proton is most acidic by removing that proton and drawing the conjugate base. So if we remove that one there, we'll have this conjugate base. If we remove any of the other ones, we'll get negative charge there, here, here, and I'm just going to draw them all in just to make this point, or here, right? So now we just want to compare where's this negative charge most stable. It's 1 unit of negative charge for each of them. It exists on carbon in each of them. The only thing that's different is in this example, that negative charge is existing on an sp hybridized carbon, and in each of these, it's existing on an sp3 hybridized carbon. So where is that negative charge most stable? Well, remember, when something is sp, it means it's 50% S character. When something is sp3, that means it's 25% S character. All right, S character, it's closer to the nucleus. What's inside the nucleus? Positive charge, the protons. So in the sp hybridized example, that negative charge is closer to positive charge. So it's being stabilized. It's being held onto. And if it's held onto, these are less basic, which means they're more stable. So an sp carbon is more electronegative than an sp3. So what that means is negative charge is more stable on this carbon, which means this is the proton that'll get removed. pKa already told us that, though. But again, I just like to show you. You don't need to memorize those things. All right, let me remove this. Okay. So we know that that is going to be the proton that is going to get removed here. So that's what's going to happen. This is going to pull that proton off. These electrons are going to get left behind. So that means we're going to have this conjugate base plus propane, because the carbon of propane just picked up the proton. So this is the conjugate acid of the base we started with, and this is the conjugate base of the acid we started with. So now we labeled everything. So now we want to know the direction of the equilibrium here. Which way is it going to go? All right, and again, we can use the pKa method. pKa of that proton is about 24. pKa of the protons on this would be about 50. Well, that means the pKa of the 24 is more acidic. That means the equilibrium is going to go away from the stronger acid. So the equilibrium is going to go that way. Or if we don't want to memorize pKa's, we can go ahead and compare the two bases. Negative charge on an sp3 hybridized carbon. Negative charge on an sp hybridized carbon. Which one handles it better? We already looked at this. This sp carbon handles a negative charge better, which means that base is more stable, which means this base, it's not going to take the proton back from that carbon. It's more stable. It's going to sit around. That means the equilibrium goes towards the more stable conjugate base. Always away from the stronger acid, towards the more stable conjugate base.